Hey, Shay, could you do me a favor? Remind us when class starts to start recording? Because I forgot today, and we're, half an hour in. So I won't be mad if you forget too, but having an extra pair of eyes trying to remember is helpful. So which trig function do you want to use here? Shay wants to use tangent. Okay. Anybody else want to use tangent, or anybody else want to use something different? It's actually interesting. Technically, right now in this problem, we could use any of them. But which one do you want to use? Well, we couldn't use any of them. We couldn't use cosecant, and we couldn't use sine. But other than that, you guys not sure or shy? Not sure is okay. You can always, guys can always say not sure. Particularly if you're not sure, it's good to say not sure, then I can talk about it. Sam likes tangent too. So let's talk about some of those options. The best way to, or not necessarily the best, but often one of the good ways to try to decide which trig function to use is we look at what we know and what we want. So in this particular case, we know the 10 feet and we want this bottom length. In reference to the angle that we know, this 10 feet is an opposite side. So whichever trig function we pick, we're going to want to use a trig function that has an opposite side in it. Sine has an opposite side, tangent has an opposite, technically cosecant and cotangent all have opposite sides in them. This side length down here that we want, this is our adjacent side. So preferably, we'd want a function that relates opposites and adjacents together. So again, going to our list of functions, tangent is opposite and adjacent. Cotangent is adjacent over opposite because it is the reciprocal of tangent, but nobody likes cotangent. You'll see, we almost never we use cotangent. We don't use cosecant much. Secant's actually really important. We'll use secant a fair amount. Almost always when we see a cotangent or a cosecant, we just immediately turn them into sines and tangents. Secant, though, does have some very important direct uses, so we'll keep it around, I guess. But if we have opposites and adjacents, the main trig function that relates opposites and adjacents is tangent. So tangent is a good choice. That would be the tangent of 50 degrees is equal to the 10 feet, the opposite, in ratio to that adjacent side, which I'm going to call little b. Technically, I'm going to call it little b. This is a good convention to know right off the bat. Call it little b because it is the side opposite angle b. So the angle b here forms the side b. So often we use uppercase letters for angles and lowercase letters for side lengths created by those angles. So that's a convention that you'll get used to. So tangent is the most straightforward and really, frankly, the best choice in this particular scenario. However, since we do know this hypotenuse is 13.05, we could technically use the hypotenuse and the side we want. The side we want is still adjacent, So if we had a function that related adjacents to hypotenuse, we could use that function. And of course, cosine is adjacent over hypotenuse. So we could use cosine. Or frankly, we could use secant just by using the reciprocal. But the reason that is not ideal is because this 13.05 is an approximation. It's a value that we came up with. Given the option, always try to use as much given data as possible, because it's not compounding our error. So if we have the option to use just the given information for this 10, great, we should use that 10. If we have to use something we computed to find something else, then we have to, so do it. But when you get to choose, always try to choose given information in your calculations. It'll keep them more accurate. For those of you who go on to take physics, you will have a lot of experience with calculating error and seeing what happens as you propagate error. As you get a small error and then you do calculations on it and more calculations on it and more calculations on it, how that error can grow and grow and grow and grow and grow. So getting into habits like this now is really handy. So take a moment, solve that for B. I don't know why I say pick. Solve that for B and tell us how far it is from A to C. I'll give you a minute or so to do that. Okay, Shay, I won't give you a minute. You have to do it really fast. We'll see if anybody argues with her. It's always good when you guys argue, because then we can talk about the conflict. We can all agree. It's boring. So yeah, let me know if you back her up or you want to argue with her. Always do feel comfortable to politely argue with each other or argue with me. We're far away in our own houses. What are we going to do? We're all perfectly safe. Do be polite and nice to everybody, but it is always a little bit harder to solve these when the variable is in the denominator. That's why I actually purposefully set this one up so that would happen for both of these examples. It does tend to throw people off a little bit. We certainly can't divide both sides by 10. If we did, we'd be left with 1 over b on this side. So that wouldn't be helpful. So this idea of multiplying over what we're trying to solve for can sometimes seem counterintuitive, but we have to get it out of the denominator. Then once we do, we can divide our tangent 50 off. Again, tangent 50 is just some number. So we can divide that number off. And 10 divided by the tangent of 50, I certainly believe that that's 8.39. And you even put feet, so I couldn't gripe at you. Though that 9 looks kind of funny, but that's okay. And always kind of when you're done, kind of check, 8.39. Does 8.39 seem reasonable for this length? You might look at the drawing and think, well, this side looks shorter than that side, but always keep in mind that diagrams are never assumed to be to scale. Just because in the diagram this is longer than that doesn't mean those values are. The homework in your book will say that a lot. Diagram not to scale. Never assume the diagram scale is reasonable. It's always fun to have a triangle that looks like that, where this is a, you say a 5, that's a 32, and that's, you know, I don't know, 28. It's like, no. It's just supposed to reference the relationship of the sides. It's not supposed to be a scale, so do be careful about that. But a nice way to kind of see if it's reasonable, one, you know, the numbers seem all in the same relative size. That 13 is a hypotenuse, so it should be the bigger of all of them. And it is, so that's good. If this length was like 1.6, I might be nervous because that would seem awfully small. But one of the tricks to keep in mind is if this is our 90-degree angle and that's a 50-degree angle, that means this is a 40-degree angle. Remember, these two angles have to add up to 90 degrees, right? Or if we were in radians, they'd have to add up to pi over 2. So this 40 is a smaller angle than that 50. Thus, that 40 creates a shorter side than this 50 creates. So this is a good thing for us to kind of keep in mind, particularly in chapter 8, it's going to become a big deal. The smallest angle here creates the smallest side. The medium-sized angle creates the medium length side. The largest angle, the 90 degrees, creates the largest side, the hypotenuse. So yeah, that 8.39 shape seems perfectly reasonable. It's smaller than the 10, but all kind of in the right scale. So I'd be happy with that answer. Anybody got any questions about any of that? Okay. We could do the same thing, of course, in radian measure. Let's say somebody gave us a triangle. Let's say, for sake of argument, we are, classic, we gotta do the classics, right? Say we're flying a kite. You all flown kites, it's springtime. We're still allowed to go outside, just not near other people, right? So go fly a kite, people will think you're crazy anyway and leave you alone. So say we're flying a kite, that kite has a 100-foot string and it's all the way out. And I'm going to show you a little bit later how to build your own angelometers, tool to measure angles. You know, it's kind of like a protractor, but a way to measure angles out in the field with simple household tools. So let's say we find in radians that this is, let's say it's 0.6 radians. So this angle here is 0.6 radians. And notice I didn't have to write radians because I didn't write degrees, so it has to be radians. While up here we have to write degrees. I'll remind you of that periodically. But while you're flying your kite, somebody comes up to you, stays outside of 6 feet, but comes up to you and says, hey, how high is that kite flying? Well, luckily you had your angelometer, so you could figure out what that angle was, and you know trig, so you could use one of these trig functions to figure out how high that is. Which trig function do you want to use? Somebody other than Shay and Sam. What trig function do you want to use to figure out this height? Jasmine or Nicholas, Dominic? Dominic wants to use sine. Well, let's check and see if sine makes sense. Sine is opposite and hypotenuse. We want the opposite and we know the hypotenuse. So I think sine's a beautiful choice. So what do we know? We know the sine of 0.6 radians is going to be equal to the opposite over the hypotenuse. So that height, h, over the hypotenuse length, 100. You might notice I never use h for hypotenuse other than here and here, and I kind of felt bad doing it. We use h for height so often, it's really good to always abbreviate hypotenuse, HYP, just because you don't want to start thinking of h as hypotenuse because that gets confusing with height. So the sine of 0.6 is h over 100. This one's nice because the variable's on top, so all we have to do is multiply over that 100. And so we're going to get 100 times the sine of 0.6. So take a moment, decide what that height is. And we'll see if it seems reasonable. $56. Okay, we'll see what anybody else gets. I actually like not having a calculator here so I can find it real fast. That way I get to be skeptical and get to be all judgmental. So see if anybody backs that up or wants to argue with that. I don't think we've heard from Jasmine or Nicholas today. You guys want to back her up or argue with her? Sam, what about you? I'm getting 1.05. Now, I like that you got 1.05. I do. And I like that you were skeptical about that. Because that probably seems weird, right? Because this height of, that being 1.05 feet off the ground, it's not going to be it's not going to be 1.5 feet off the ground. So being skeptical of that answer is very, very reasonable. What might be the issue that would make the trig function throw out a value that doesn't quite make sense? You're using radians, right? So, Sam, if you're still in degree mode, then the calculator thought this was 0.6 degrees. So the calculator was saying, okay, 0.6 degrees is really tiny of an angle. So it gave you a very tiny length. Does that make sense? Yeah. So again, do be careful. We switched from degrees to radians, so we got to switch modes. Shay, you're 56, that being 56 feet high. 56, quite reasonable, actually. So I very much believe that 56.46 feet. And of course, you'd want a sentence. The kite is 50 feet high. Always answer your word problems in sentences. Use better writing than that. But so yeah, Dominic, if we're in radian modes, as we should be, then Shay's answer is right. So Sam, I like that you were skeptical of that. You thought about your answer and said that answer seemed wrong. But do be careful. That mode is often going to cause that to happen, particularly if you haven't used your calculator in a while and you pick it up and it just happened to be in whatever mode it was in before. So do be sure you're careful about that. Let's see. And again, for our intuition, like 0.6 is a pretty small number. So if we're still trying to build that intuition about radian measure, like, how much should that be? Should it be a lot? Is this 56 fairly reasonable? Well, remember that for a particular, I'll change that. For a particular radius r, that arc length, if this radius r goes up that same distance as an arc length, so say about there, where this radius is the same as that arc length. I don't, how accurate my drawing is probably not terribly accurate, but it's not too bad. If this length s is the same as that length r, then this is 1 radian. So 0.6 radians is going to be 60% of this. So it's going out at, now that looks more like 50%, it's a little higher than that. So it's going out at, roughly, again, very rough diagram, but that 0.6 radians is about there. So if that's 100 and that's 56, does that seem reasonable in scale? Hopefully it does. It takes a while to get comfortable with the idea of 0.6 radians. How much is that? Where does that lie on my circle? That's one of the reasons I want you guys to be practicing that construction that we did the other day. We might even have some sort of quiz-like object in reference to it, where you guys were going, 0 and pi over 2 and pi and 3 pi over 2, right? You remember us doing this together? I really do want you to practice this, not memorize this. Too much information to memorize effectively, but build it. As long as we know there's 2 pi all the way around, then that's half of it. Pi over 2 is half of that. Pi over 4 is half of that. Instead of taking a half of it, take a third of it to get to the pi over 6. And then we can do that counting around to build all the others. So we'll practice that some more, but make sure you're practicing that on your own. I'm starting to build this intuition. Fair? And even just objects like that, that is pi over 4. Well, pi is approximately 3, right? So this is about 3/4. Pi over 6. Well, pi, again, a little more than 3, so this is a little more than a half. So that 0.6, well, 0.6 is between a half and 0.75. So that 0.6 radians is going to be right in between there. With practice and experience, you can get to a point that you visualize radians really well if you try to embrace them. You try to keep them at arm's length and they're going to be weird forever. So dive in, play with them, make them yours. Okay? Any questions about any of this right now? What I want to do tomorrow, I gotta let you guys go today, but what I want to do tomorrow is talk about these standard angles that we've found. It's pi over 6, pi over 4, pi over 3. And their multiples, the 30, 60s, and 45s. I want to talk about why there are standard angles, what makes them so important, and do a little bit of geometry to build some tools that we're going to need. Okay, so you don't want to miss that. It's some good tools. If you do come up with any questions or need anything, let me know. And if there's nothing else I can do for you today, have a wonderful day. Sam, say hi to Tom for me if you talk to him. Preferably tease him mercilessly if you have a chance, but Dominic, is there anything you need before I trundle off? Nope. I'm going to assume that's nope. Okay. I'll see you next time.